Hi, my name is Peter Abugri and I'm presenting on statistical machine learning. The first data to be looked at is a data made up of X and Y, where X is the independent variable and Y the dependent variable. So I first looked at the relationship between X and Y by plotting the scatter plot, and it was quite clear that it follows nonlinear pattern or relationship. And the problem of this was regression problem. And I looked at the theoretical framework of this data, and then the functional space. Functional space of this data set was a polynomial functional space. So I looked at the loss function, the theoretical risk, and the Bayesian learning, which is always the predictive function in a regression problem. And the empirical risk, I went further. All these I estimated using the ordinary least square estimator. And few of the properties are the linearity, the best linear unbiased estimator, sensitive to outliers. Part 3, question 3, I look at the data. So the data was further divided into some subsections to find the optimal degree for the optimal degree for the problem. And it was found that degree 10 is the best optimal. So I plotted the cross-validation error against the empirical risk. It was quite clear that as the degree increases, the error margin also decreases. So I plotted the model. So I compared the model. So the simplest model shows a straight line as shown. Likewise, the optimal model. So the optimal model and the complex model was quite almost on the same line, but the optimal model was quite better since it can be used to generalize any data, of which the complex model cannot be used as such. So the interpretation of the box plot will also plot it to look at the relationship between these three models. I further look at the analysis of variance to look at the best model, and the p-value was quite small, f-value over 3,374. Likewise, the confidence band, I also looked at that, and the mathematical expression for the confidence band was also estimated. And exercise 2 was a data set from R, which was a spam data made up of 4,600 email spam or non-spam and 57 variables. And I look at the distribution, and the spam category has a noticeable higher value than non-spam, indicating greater frequency or proportion. So comment on ROC. So the ROC curves was also plotted, and it provides visual comparison to correctly classify the two cases, either spam or non-spam. And so the ROC curves likely show that LDA performs better when class distribution vary and naive base remains competitive, aligning with theoretical expectation based on each model's assumption. So we plotted the comparative plots of the models. So based on 4 models was plotted. That's the linear discriminant analysis, quadratic discriminant analysis, and naive Bayes theorem, and Fisher linear discriminant. So based on these comparisons, the linear discriminant analysis seems to be the most considerable model, as shown in the box plot. So the reason why the linear discriminant analysis was because it showed us the lowest median test error and relatively tight interquartile range, indicating consistent performance across applications. LDA assumes linearity and equal variance across classes, making it less complex and more stable, especially when since these assumptions, or assuming that these assumptions are hold. So after comparing all these, the LDA model was quite correct to be considered. Thank you.